All right, we're picking up here with 7.4, properties of logarithms. So in last video, we talked about what logarithms were, but now we're going to discuss a little bit more about some of the properties they have. We're not solving any equations yet. We'll get to that when we do 7.5. But these properties that we're going to learn are going to help us with those equations later on. So let's talk a little bit about these. Now, some of these properties are related to properties we learned back in the day. For example, we talked about, having x to the second power times x to the fifth power being x to the seventh power. And the weird thing about this is, we're multiplying here, right? It's x to the second times x to the fifth. But what did we do with the exponents? We didn't multiply the exponents. We added the exponents. And so we kind of have that connection as well with logarithms. Logarithms are the exponents. But when we add logarithms, the thing is we'll end up really multiplying the values within them to combine them together. You'll see what I mean in this first property. So the product property of logarithms. This is the one where, it talks about that connection between multiplying things with these exponents, but really adding the exponents. But this is like the logarithm version of it. So let me give you a numeric example to kind of explain what this looks like. So I'm just going to make something up here. Let's say log base 4 of, 6 plus log base 4 of 5. All right. So the thing is, both of these logarithms have to have the same base for it to work. So to add logarithms together at all, at least put them together into a single logarithm, you have to have that same base, base of 4 in this case, just because I decided to just pick 4. But even though you're technically adding logarithms, we're not really going to add anything together here. To combine this into one logarithm with a base 4, of course, I'm not going to add 6 and 5. I'm actually going to multiply 6 and 5. 6 times 5 to make 30. So these two logarithms can add together, or combine, I guess, really together to make this logarithm. So it's plus, you're adding logarithms, but really you're going to multiply these values within them. So it's kind of weird. It's like, why would we do that? But the reason why we do that, same reason why we added them here. So remember, the exponents you technically added, even though really what's going on is multiplying. Well, logarithms are exponents. So this is an exponent plus another exponent. So that means that the bases are being multiplied together. So that's why we ended up multiplying the 6 and 5. So, and if you need proof, let me back out of this real quick, pull up my handy calculator. Let's type this in. I got a new calculator, by the way. It's cool. Anyway, it's the same thing, but it looks different. If I type in the same problem that I just did, so let's go to math. Let's go to our log base. So we can actually type in the base of 4 that I picked. I picked log base 4 of 6, and I added it to the log base 4 of 5. And let's just see what this equals real quick. So it equals that number, 2.45. Fantastic, whatever. That's cool. Let's see if the same number we get when we do the log base 4 of 30. Because remember, we said that these would be the same thing as log base 4 of 30. Okay, I wish this was a little bigger because I'm accidentally pressing the wrong buttons there. All right, log base 4 of 30. There you go. Same thing. So it seems weird, right? But that's how it works, and it's connected back to that property we talked about before. Go back to this. So that was my numeric example. This already has another numeric example, but I just wanted to make my own. But there's another one. Does the same thing. Algebraically, though, this is what's happening. So you have a log with the same base. You'll notice both of them have a base of b, and you're adding these logarithms, but you're actually going to take the m and the n and multiply them together when you want to combine these two separate logs into a single log. It's kind of weird, but that's the property. So let's get into, let's do a couple examples just for practice, I guess. So log base 4 of 2 plus log base 4 of 32. So we're adding logarithms, but remember, you're not going to add anything together here. You're going to multiply the values in these logs. So 2 times 32 makes 64. Now, we're not necessarily done yet because although we've combined these logs into one log, this is correct and all, but this equals a number, and I want to go ahead and answer what number that is. So remember, to do this in your head without having to use a calculator, sometimes you have to use a calculator, but in a problem like this, we should be able to do this logarithm in our head. And here's how you would do it. So think of this logarithm as an exponential equation, right? Think about how you converted it. We talked about that in the last video, so if you need to go back to the last video to refresh your memory about this, you can. But to convert this logarithm back into an exponent, this would mean that we have the base of 4 raised to some power. That's what the question mark here is. That's what we're supposed to equal. 4 raised to some power, try to make that a question mark, equals that 64 that I see. So to know what this number is that this logarithm equals, I have to think, well, what power goes on 4 to make 64? Is it 4 to the second power? Is it 2? No, because 4 to the second power is 16. It's actually 4 to the third power. So if you know that 4 to the third power is 64, then you know that the log base 4 of 64 is equal to 3. Okay. With E, again, it's very much the same idea. So we got the logs. They have the same base of 1/3. But you're going to multiply the 27 and 1/9 together. 27 times 1/9 is the same as just 27 divided by 9. And 27 divided by 9 is 3. So it's a log base 1/3 of 3. And that equals a number as well. But I'm not as skilled at doing that one in my head, so I'd type that in the calculator. But we're going to go ahead and move on. This one here, log base 5 of 625. Log base 5 of 25. So, of course, they both have a base 5, so that's cool. But when you multiply these together, because you're adding logarithms, remember, but you're really multiplying these numbers. 625 times 25 is, if I remember correctly, 15,625. Not that I know that off the top of my head, but I worked that out earlier in class, so I think I remember that being right. And by the way, you might not be able to do this one in your head, but it is 6 this actually equals. Because 5 to the 6th power, again, not that you would memorize that, but 5 to the 6th power is 15,625, which is kind of cool to know. And the last one here, we have a log base 4, or log base 6 of 4 and a log base 6 of 9 combines to make a log base 6 of 4 times 9, and 4 times 9 is 36. And we can actually answer that because, well, think mathematically, think in your head, 6 to some power equals 36. Well, 6 to what power? I think we all know that. 6 to the second power is 36. So this is equal to 2. All right, let's get into the subtracting one. So it's based off of the property we learned months ago. If I have, let's say, x to the 5th divided by x to the 2nd, technically we're dividing, right? It's x to the 5th divided by x to the 2nd. But we didn't do division. We didn't do 5 divided by 2. The exponents just subtracted because the x's canceled out. So we're just taking things away, thus subtracting. So there's a connection here that, yes, in the grand scheme of things, it's division. But as far as the exponents are concerned, the exponents didn't do division. The exponents did subtraction. And we see that connection here with logarithms as well. So it's very similar to what we were just doing. Let's make up my own example. So let's say I have log base 5 of 32 minus, so subtraction. Okay, this is the difference. Subtraction. When you see subtraction, this is what will happen. You got log base 5 of, I don't know. Let's just pick 8. All right. So let me see if I can fix that. There we go. So you're subtracting logarithms, and that's all well and nice, but you're not actually going to subtract. And again, this, just like the last one, these have to have the same base. So these are both with a base of 5. If they didn't have the same base, we couldn't combine them. But what we're going to do with the numbers between these is actually not subtract, it's actually divide. So when you're adding logarithms, you're going to multiply those values, but when you're subtracting logarithms, you're going to divide those values. So 32 divided by 8 makes 4. So log base 5 of 4. And yeah, that is a number, but it's probably some decimal. So we can't do that in our heads, but you could type that in the calculator to see what that actually ends up equaling. Let me go ahead and click ahead so we can see the algebraic version of it. So again, this just says 2 logs, right? Both of these logs have the same base. You're subtracting these logs, but when you're subtracting these logs, you're taking m and n and dividing them. You're not actually subtracting the m and the n. You're dividing m divided by n. So it's very much the same thing as the last property we just talked about with the addition. It's just sort of the exact opposite of it. So just for practice, log base 2 of 32 minus log base 2 of 4. This will combine because they're both log base 2. But when we combine these, again, we're not subtracting these values, we're dividing these values. 32 divided by 4 is 8. So that's combining it into one logarithm, but we can actually do this again. We can solve this one without a calculator. To solve this one, you just have to think, okay, 2 to some power equals 8. Well, what is that power? What is that exponent here? 2 to the third power equals 8. So it's going to just be, this is all just equal to 3. For J, the next one, we've got log base 5 of 100 minus log base 5 of 4. So that's going to combine to give us a log base 5 of 100 divided by 4, which is 25. And again, we can do this one. We should be able to do this one in our heads. 5 to what power equals 25? Well, in this case, it's 5 to the second power, right? 5 squared is 25. So the answer there is 2. Let's look at this last one. Log base 7 of 49 minus log base 7 of 7. So again, you combine them, they get the log base 7. And 49 divided by 7 is 7. And we should know this. Whenever these values are the same, this just equals 1. And it equals 1 because 7 to the first power equals 7. But I do want to show you something real quick, just so that you kind of have a better vision of this problem, better understanding of it. Notice here, this first logarithm, we actually know what number this is, because if we know 7 to some power equals 49, well, what is that exponent? 7 to what power? Well, I think you guys know it's 7 to the second power, right? This logarithm is equal to 2. You can type it in your calculator if you don't believe me, but like I said, we should be able to do that one in our heads. And this is minus log base 7 of 7. Well, we just talked about that when these values are the same, that this log is equal to 1. So really this equation is 2 minus 1, and 2 minus 1 equals 1, which is what we got before. And you can actually see that in H as well. We can do this one in our head. This one is 6, right here, the log base 2 of 32, because 2 to the 6th power is 32. So this logarithm is just 6. We know this because 2 to what power equals 4? Well, it's 2 to the second power, so I know that this is equal to 2. Oh, I'm sorry, this is 5, by the way. I messed that up. Because 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16, and 16 times 2 is 32. So you had 2 to the 5th power, right? 2 times, that's 5 2's multiplied together. So my bad, I said 6, but I meant 5. So this is really 5. This is really 2, and 5 minus 2 is 3. It all makes sense in the end. It all adds up. All right, there's one more property I want to talk about. This property is very useful when it comes to solving the equations we'll do in the next section. So pay close attention. It's the power property of logarithms. So this property is kind of related to when you have, let's say, x to the second power to the 5th power, how this ends up being x to the 10th power. So you notice we have another exponent, right? 2 exponents, an exponent with an exponent. What did we do? We multiplied those values together. So the concept of having that connection between the exponent And multiplication is sort of the same thing we see with the logarithms here as well. So what we're going to see, here's an algebraic example. That's the property itself, but let me go ahead and just give you a numeric example. Let's say we have log base 3 of, let's say, 27. Right? This is a normal logarithm. We've seen this logarithm before. We have the log, we've got the base value, we've got the number within the logarithm. But what if we put an exponent on this? Let's say it's 27 squared. Well, now it looks weird, right? We haven't seen exponents on our logarithms before. We've just seen the logarithm. We never saw an exponent before now. But it's very simple. I can relocate this exponent because having that exponent there is very inconvenient for us when it comes to a lot of our problems. So this property allows us to take the exponent and move it to the front of this logarithm. And instead of it being there, it'll be up front, and it'll now be 2 times the logarithm 327. It's not 2 plus the log, it's not 2 minus the log, it's 2 times. So it's always going to be multiplication. But all you're essentially doing, and you can see that here, is taking whatever the exponent is, relocating it to the front of the logarithm, right? And now you don't have the exponent up there, you just have the exponent in front. And again, the reason why we can do that is because when you have an exponent with another exponent, what exactly do those exponents do? They just multiply themselves together. That's exactly what's happening here with these logarithms. Okay, seems kind of weird, but it's one of those properties. It's a very useful property as well. You're going to see us use that property a lot when we get to solving equations. So it's very simple, but very powerful. So let's go ahead and answer a few of these just real quick. So notice we got log base 3 of 81 to the second power. What I'm going to first do is I'm going to move this exponent, because I don't want that exponent 2 there. I'm going to move the exponent to the front. So instead of having it up there, it'll be in front of the log. It'll be 2 times the log base 3 of 81. And ultimately, this is 8, by the way, because the log base 3 of 81 is 4, because 3 to the 4th power is 81. And then 2 times 4 is what makes 8. But again, you can type that in the calculator if you really wanted to. But you should be able to try to do those on your own as best you can. So notice in the second problem, I have the 3 as the exponent. Well, I'm just going to move that 3 over to the front. So it'll be 3 times the log base 5 of 1/5. I'm not going to worry about getting that value right now. We're just going to move on. Take this 4, move it to the front. So it's the same as 4 times log 10. We can solve this one pretty easily in our heads, if you remember. So notice there's no base here. It's just log 10. Well, we talked about this in the last video. If there's no base, it means the base is 10. So what's this number? Log base 10 of 10. That number is 1. Because remember, if these values match, then that whole logarithm is 1. So this equation is really 4 times 1, which equals 4. And then this last one, we're going to move this 2 to the front. It'll become 2 times log base 5 of 25. And again, we can do this one because 5 to what power equals 25? Well, again, we know that. We know 5 to the second power is 25. So I know that this logarithm here is just 2. So 2 times 2 ends up making 4 for that answer. All right. I do quickly want to just go ahead and throw this in there as well. We're going to just skip this real quick. The change of base formula, this is really more useful if you don't have a graphing calculator. If you just have a regular scientific calculator, nothing wrong with that. But the regular scientific calculators, let me go ahead and show you on mine. So my calculator is a graphing calculator. So I have the capability of going into this math menu that you saw me do earlier and being able to choose this option where I can type in any base I wanted to, like 4 earlier, like 6 just now. But the regular calculators, just your standard calculator, doesn't have that option. It just has the regular log button, which you can see here on this calculator too. It doesn't give you the option to put a base in. It uses the common log. It just uses a log with a base 10. So remember, because I don't see a base there, I know that that base is 10. So how can we do these types of logarithms, like log with these weird bases like log base 4, right? How can I do that in a regular calculator if I can't type it in that way? Well, the change of base formula is useful for that, because all you're really doing, got it. Let's kind of open this up so I can write on this a little bit better. So let's take an example. Let's say that we had the log base 3 of 8. Okay. So how this works is this x, right? Which is 8 in this case, is, well, okay, I don't know how to say this kind of easily. See how these have a in it? You see, it's called change of base formula because the base is, something weird now, like 3 in this example, but we're going to change it to whatever we want. But, typically we're going to change it to 10, a base of 10, because obviously those are common logarithms and a regular calculator can use common logarithms. So really, when you see this a here, it's really more or less the base 10, okay? I mean, it can be anything. It doesn't have to be 10, but we're going to use 10 because, like I said, every calculator has the capability of doing a base 10 because that's the common logarithm. So really, a better way of looking at this formula, instead of seeing the a there, is just your common logarithm of x over your common logarithm of b. So in that case, it's going to be the common logarithm of 8, so log 8, divided by the common logarithm of that original base, log 3. And I can type both of those in a regular calculator. I don't have to use any special feature. So log base 3 of 8 is the same thing as log 8 divided by log 3 as common logs. And we can do that real quick on the calculator just for proof. So let's get a benchmark. Let's go type this in just real quick. Using the fancy way, just to prove that it works, right? Log base 3, oops, too much there. Log base 3 of 8, let's just see what it equals. It's that, 1.89, right? But if I don't have that capability to type that base in myself, I can use a change of base formula, which we just wrote, using the common logarithm, log 8, divided by, again, common logarithm, base of 3, equals the same exact thing. So notice I didn't have to use that fancy feature. I didn't have to go into the math menu and choose that log base. I just used your standard common log button, right? So that's what the change of base formula does. It's just basically a common log of this divided by the common log of that. And you can see that here in this example, log base 4 of 8 is the common log of 8 over the common log of 4. This one would be a common log of 27 over a common log of 9. And this one would be a common log of 16 over a common log of 8. So it's just basically this number on top, the little number on bottom, using common logs, and you're all set. You're good to go. I just wanted to show you that real quick because it's very useful, particularly for people who don't have a graphing calculator. Graphing calculators are great, but they're not always cracked up what they, or people make them out to be. They're good, but you can do some of the same stuff on a regular calculator too. So just keep that in mind. That's going to be it because I know this video is kind of long, but I will see you guys in the next one. Peace out. Why did I say peace out? That's stupid. Bye.